Hey, hello everybody. Today we're going to look at 9.2 ellipses. So we just did circles. Now we're going to move on to look at more oval type shapes or ellipses. And this is where that vocabulary of foci or focus come into play. And there's going to be a couple other pieces of vocabulary we're going to encounter along the way. We're going to need to focus in on that for a second when we get to it. But what's important to realize about an ellipse is, unlike a circle where you have a single radius and all of the points that comprise the circle are equidistant from that radius, in an ellipse we have two focus points, here and here, and the distances from one focus to a specific spot on the ellipse, and the distance from another focus to a specific spot on the ellipse. The sum of those two distances will always form a specific constant. So let's continue. Now here's a little bit more vocabulary for you. When we're looking at an ellipse, obviously we have one way that's wider than another, and we have different names for the axis, that axis of symmetry that goes through the ellipse, whether it's going the long way or whether it's going the shorter way. And it's pretty intuitive to think, the longer way is the major axis. Regardless of which way the ellipse is oriented, the longer way is the major axis. The shorter way is the minor. Major meaning more, minor meaning less. And so that should be pretty intuitive vocabulary. But with this picture here, I actually want to kind of throw a little bit more information at you, at the way that we're going to kind of depict some of the spaces on an ellipse. I'm going to put two more dots in here, one here and one here, to represent the foci. And what I want to do is label some of this ellipse with specific areas. So let's call the area from the center of the vertex, center of the ellipse, to one of the foci. Let's consider that like a length of c. And then the length from the center to along the minor axis to the edge, we'll call that a length of b. And let's call a length from the center all the way to along the major axis to the edge, we'll call that, so it's going to be this much, this entire thing. We'll call that A. Alright, nice and easy, A, B, and C. Now the reason some of these things are going to be important is the way that they kind of relate to each other. And what you might be able to see is this little triangle that's kind of being formed here. If I draw a specific line to this point from the foci. Now, what's interesting about choosing this particular point is that this particular point creates equivalent distances here, particularly like a distance 1 and a distance 2. D1 would be equal to D2. Oops. D2. Now that's not always the case. Obviously, if I moved to this point over here, D1 would have been way larger than D2. But in this case, they are. And I'm just doing that for simplicity's sake. And remember that D1 plus D2, the two distances from any particular, from the foci to any particular point, D1 plus D2, always equals some constant number. And it turns out that this constant number is equivalent to what we consider to be 2 of A. So really, it's the length of the major axis. And that's a very, very important relationship that happens in ellipses. And there's one other piece, which is, say I didn't want to call this D1 and D2. I wanted to actually, give some sort of name based upon the A, B, and C that we talked about before. Technically, this is the hypotenuse of a triangle with B and C. So I could, rewrite that distance as the square root of B squared plus C squared. That's just another way that I could rewrite that distance D2. And if I wanted to just create a re-representation of these two equations, I have two of these distances, so there's two of them, and that equals 2a. And this relationship brings about a lot of different variations to it, just like you can vary the Pythagorean theorem a lot. So we can rewrite this so it says something like b squared plus c squared equals a squared. And this is going to be kind of like your simplified version. And you can rewrite it based on if you know b, if you know c, if you know a. It's going to come in very handy. So keep in mind this relationship as we go through and we move on to some of the examples. Alright, and again, formula page, which I'm sure kind of just knocks you all back and says, I don't even want to deal with this because it's craziness. But let's just look at the first equation right here. Just stick with me on that. If you need to cover up all the rest of this, do it. Just this first equation looks very, 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 very much like a circle, right? If I were to ignore the bottom of this, it would be a circle with radius 1, right? Now, the reason that I'm keeping in this a squared and this b squared, or rather I'm adding them, is to tell me, am I shifting this circle so that it's wider? Am I shifting this circle so it's taller? The a and the b values are what's signifying the major and minor axis, just like I showed on the last slide, where we titled the major axis with an A and we titled the minor axis with a B. So it kind of makes sense that in this case, where the major axis is horizontal, the A, that major axis value, corresponds to the x's. Right? So that means that the entire ellipse is going to be wider. And then if I look at this other one where the major axis is supposed to be vertical, that A value is now paired up with the y's, meaning that major axis is going to be longer in the direction of the y's. Now, if I come back to this equation right here, this is exactly what we just said in that relationship on the previous page. We had written it slightly differently, which is partially what I said. You can rewrite them over and over and over. I think we wrote b squared plus c squared equals a squared. And really the only difference between this is that I've taken b squared and moved it to the other side, and that's this equation over here. And then lastly, what happens when the origin is at 0, 0? Well, what happens if my h and my k, my center of the ellipse, is at 0? Well, those h's and those k's just go away, and that makes the equation a lot simpler. Right? So hopefully this page doesn't look too scary anymore. It's basically one equation for a, like a fat ellipse horizontally, one equation for a really tall ellipse, the relationships that we were talking about between the major minor axis and the foci, and then lastly the equations when you're centered at the origin. And these just some depictions of the things that I was talking about. Again, when you have the a value, which represents that major axis corresponding to the x values, you're looking at more like a fat type ellipse. When you have that a value that represents the major axis corresponding with the y's, you're looking at more of like a tall, slender ellipse. Now let's look at the first example where I want to create the standard form of an ellipse that has specific foci, 0, 1, 4, 1. And we also know that the major axis has length 6. Okay, so there's a lot of information there. Only really 3 sets of numbers, but there is a lot of information there that we can go for. So let's see what we can do. In order to create the equation for the ellipse, I do need the center. So I need to find the midpoint between 0, 1 and 4, 1. That's kind of priority number 1. Now with numbers like this, it's really not that difficult, but what we would be doing is the midpoint formula. So you might want to go back and double check on that, make sure that you know that very well. But the center we can see easily from this one is 2, 1. Right? Now, what we need to do is figure out what is that C value. What is the C value is supposed to be the distance from the center point to the foci. Right, so the distance from the center 2, 1 to one of the foci 4, 1 should be 2. Do I know anything else? Well, I know that the major axis has length of 6. The major axis is twice the value of A. Right? We actually have that depicted here. A is just one side of the major axis. So we know A equals 3. And then what else do I need for the equation? I need B. Okay, so this is where that relationship is going to come into play. I know that I can get B simply by saying the square root of A squared minus C squared. So in this case, that means the square root of 9 minus 4, which means the square root of 5. So my B value is going to be a square root of 5. Alrighty, now do I have enough to create my equation? Yes, I think I do. It's going to be x minus h, which over here, the center is going to be a 2, and that's going to be squared, and that's over. Is this going wide or is it going tall? It's going wide, so I want the a value underneath here, and I want the a value squared, so 3 squared, and then plus y minus the k value, which is a 1, squared over the b value squared, the square root of 5 squared, equals 1. And there you have it. Let's see, let's take a look at exercise 31 from section 9.2. Take a look at that, try it on your own. I'll check it out when you come into class next time. And then once you're done with that, we can move on to our next example. Alright, now with example 2, what we're doing is sketching an ellipse based upon a specific equation. And of course, again, just like circles and parabolas, we have not been given the equation in a way where we can pull the information out of it nicely. So we're given it as 4x squared plus y squared equals 36. What I really want is it to be in that form where it says, you know, x minus h squared over a squared, or maybe b squared, plus y minus k squared over b squared, or maybe a squared, equals 1. So how can I make that happen in this case? Well, my biggest issue that I'm seeing is I have a 36 on the right side of the equation, and what I should have is a 1. So I'm just going to go ahead right off the bat and divide everything by 36. That's 4x squared over 36 plus y squared over 36 equals 1. Nice. Okay, so I've managed to make some change. Now, why don't I reduce this fraction over here, so I can just get x squared over 9 plus y squared over 36. Now things are starting to look a little bit better. Looks like on the top I kind of have it all set. The only thing that I need to realize here is I'm not going to get an x minus h squared. I'm not going to get a y minus k squared because my hk, my center point, is at 0. That's why it's not looking like that. But then on the bottom now, I need to be sure that I'm putting it in terms of a squared and b squared. So x squared over 3 squared plus y squared over 6 squared equals 1. Cool. So now which number is larger? This number is larger. This is my major axis. My major axis is on the y. So what does that tell me about the equation? It means that this equation is going to be going a lot more vertical than it is horizontal. So when I go to graph this thing, I know I'm going to center it at 0, 0. It is going to be 6 units up as well as 6 units down. It's going to be 3 units to the left as well as 3 units to the right. And then I'll basically have my entire ellipse graphed. Let's take a look. This is exactly what you should get right here. Center at 0, 0. The a value being with the y's suggests that I have to move up 6 to 0, 6 for a point. And I also have to move down to 0, negative 6 for a point. The 3, for the b value being with the x's, means I'm going to the right to 3 and to the left to negative 3. Draw a smooth line around the entire thing, and you've got it down. Let's try exercise 37. And when you're all set with that, we can move on to our next example. But please do exercise 37. We'll check it out in class, and then we will move on. The last thing that I want to talk about, and it's going to be very, very brief, is the idea of eccentricity. And eccentricity, in its simplest form, is basically how much of an ellipse is this ellipse? How elliptical is this ellipse? And one of the reasons that it was so difficult for early astronomers to discover that orbits in space are elliptical, or at least that some of the orbits in space are elliptical, is because they're not that elliptical. They seem quite circular. So there's this word for it, which is eccentricity, which describes just how elliptical an orbit is. So the eccentricity of a specific ellipse is just given by a ratio of that c value that we talked about, the distance from the center to one of the foci, over the a value, which is that distance from the center along the major axis to one of the ends, one of the vertices. Alright, so just that ratio will give you an expression of how elliptical or how radical that ellipse is. And that is it for today. I will see you guys next time.